Let A be the first term of the geometric progression, and let R be the common ratio. And therefore the first three terms of the geometric series are A, AR, and AR square. Now we're given that the sum of these three terms is equal to alpha times S. Taking A common on the left hand side, we get A times 1 plus R square is equal to alpha S. Let's denote this by 1. We are also given that the sum of squares of these three terms is S square. Taking A square common on the left hand side, we get A square times 1 plus R square plus R raised to power 4 is equal to S square. Let's denote this by 2. Now we divide the square of 1 by 2 to get, on the left hand side, A square times 1 plus R square whole square divided by A square times 1 plus R square plus R raised to power 4 is equal to, on the right hand side, alpha square times S square in the numerator and S square in the denominator. This results in the elimination of A and S, and therefore alpha square is equal to 1 plus R square whole square divided by 1 plus R square plus R raised to the power 4. Now the denominator can be expressed as 1 plus R square whole square minus R square, and therefore alpha square simplifies to 1 plus R square whole square divided by 1 plus R square plus R times 1 plus R square minus R. Cancelling common terms and cross multiplying, alpha square times 1 plus R square minus R is equal to 1 plus R square. Opening up the left hand side and moving all terms to the left and collecting terms with like powers of R, we get alpha square minus 1 times R square minus 1 plus alpha square times R plus alpha square minus 1 is equal to 0. Now this is a quadratic in R, and since R is real, therefore the discriminant of this equation needs to be greater than equal to 0. The discriminant is equal to the square of the coefficient of the middle term, which is minus 1 plus alpha square of this minus 4 times the coefficient of R square times the constant term will be greater than equal to 0. This implies that alpha square plus 1 whole square minus 2 times alpha square minus 1 whole square is greater than equal to 0. This is of the form a square minus b square and is therefore equal to a minus b times a plus b. So in this case, the left hand side becomes alpha square plus 1 plus 2 times alpha square minus 1 times alpha square plus 1 minus 2 times alpha square minus 1, and this should be greater than equal to 0. The left hand side can be written as 3 alpha square minus 1 times minus alpha square plus 3, and this is greater than equal to 0. Dividing by 3 and multiplying by minus 1, this inequality is equivalent to alpha square minus 1 upon 3 times alpha square minus 3 is less than equal to 0, which is possible only when alpha square lies between 1 upon 3 and 3, which is the required answer.